So now in the yesterday's session, we try to understand the structural importance of the MOSFET. So basically, we try to see how exactly the MOSFET's structure looks, and we saw that the MOSFET has got the three terminals. Today, we'll continue from there where we left yesterday, and we'll try to understand a little more deeper on how exactly MOSFET works, so that whenever we try to work onto these MOSFETs in the circuit perspective, we should be in a condition to understand what sort of voltages I should be giving and what sort of voltages would impact the entire working of the MOSFET. So let us try to look into that. So I'll draw the MOSFET with the oxide layer and then metal layer. So I have this as source, gate, drain. This is my N well, and this is my P substrate or P type body. Fine. So yesterday we tried to understand what sort of voltage should be given. Now, because this is an N well, we have the source and drains are having N type contents. That means for sure there will be an N channel that is going to form. And to ensure N channel is formed, I should have a positive voltages towards the gate. That means my connectivity should look something like this. And this is my VGS. Fine. So yesterday I told we have to apply certain voltage. So let's try to understand the conditions. So first is basically you have to apply VGS till a proper channel is formed, and that means we have to apply this VGS till a voltage called as VTH or threshold voltage. So basically, if I try to give you a simple analogy, let's say that we are going to build a bridge here, let's say from point A to point B. And once the bridge is completely built, then only people can move from one end to another end. But the thing is, the bridge can be said that it is completely built only when I see that there is a complete construction happening from the point A to B. That's when I say the bridge has been built. And whenever I say that, see, complete construction in the sense the bridge is built, but let's say that the painting has not been done, some beautification has not been done, but bridge is built. That means it has become ready to ensure the traveling can happen. So that is that particular time when we say that bridge is built. The rest all works, whatever that happens on the bridge, are the extra work that is going to add the beautification to the bridge. It is not going to enhance the property of the bridge, but basically the core property of the bridge has been achieved the moment we build the bridge. So that point at which the bridge is completed, or that point when we say that there is a proper channel is being formed, we say that the MOSFET is on. So we say that the MOSFET is. So I say that the condition would be whenever VGS is greater than or equal to VTH, I can say that my MOSFET is on. So this is one of the prime condition that we have to remember. Now, once we understand the MOSFET is on, once we say that it is on, now let's try to understand what will happen to ensure the flow of current. Like yesterday I told, to ensure the flow of current happen, I have to apply another voltage, which is my VDS. Now, first thing is, what will happen if I further increase VGS? Will there be any changes that is happening to the bridge or the channel? Let's try to understand. The condition here is if VGS is kept increasing forever. what will happen? Nothing will happen, in the sense you are just simply pushing a lot of electrons over here, and they are going to hop from one end to another end through this channel, and at the same time some of the positive charges that they are going to come and accumulate over here, which are going to attract more number of electrons. That means the channel is going to strengthen, or the channel is going to increase in its width. Lengthwise the channel won't increase because length is fixed, but the width wise it is going to increase. How exactly it increases width wise? See, this is how basically I can say. In fact, width wise, and even width wise is also a fixed. Thickness wise it is going to increase. So basically I can say, in terms of its three-dimensional structure, so this is, let's say this is source and drain. So already some sort of, see how exactly that in a three-dimensional figure looks. So let's say the electrons may have been formed like this. Now this is a connectivity that has happened from source to drain. So here is basically is your source, and let's say here is your drain. The three-dimensional structure I'm talking. Okay. Now, initially, let's say at threshold voltage, some channels have some electrons have been aligned in this way, and the channel is formed. And whatever the extra electrons that come to the source, they hop from one place to another place with the help of these electrons, and they move to the drain. Now, if you increase this VGS, if VGS is further increased, what will happen? Some more extra holes they come on top of this gate, and they attract few more electrons, and they are again settled over here. So like that, what you can see. So this is basically length. Length is of course fixed, and this is basically my width. Let me mark it. So this is my width. So basically, and this is thickness. So basically, if you keep on increasing the voltage VGS, the width of the channel is going to increase. Earlier, see, this is my width of the channel. So basically, this was my width. Now, if I increase VGS further, it is going to accumulate more positive charges over here. Basically, the positive voltage is going to ensure it is going to attract more number of electrons, and they go and accumulate beneath this channel, and the width keep on increasing. So basically, what will happen? Width of channel increases. That is another point. And in the same time, I can also say, even after increasing VGS, what will happen? Thickness of channel also increases. That means here effectively you are not making any progress. You are just merely increasing the width, or you are making the channel more and more stronger. Apart from that, we are not actually making any particular progress over here in terms of the flow of current, because what actually happened, we here we just want to ensure when is the current is going to flow, because when we say MOSFET is going to behave as a switch, that is it is now turned on, that means the channel has been formed. So in all these conditions I can say MOSFET is on when VGS is greater than or equal to VT. So if this condition is met, I can say that the MOSFET is turned on. Once my MOSFET is turned on, it should not happen that I keep on turning on this MOSFET again and again. It is basically, if it is turned on, a proper channel has been built, we have to stop increasing VGS. And nothing will happen if I keep on increasing VGS. It is just merely going to strengthen the channel. And again, in terms of circuit perspective, if you increase any voltages, there will be a lot of power consumption also. The drop will increase. So that's why you better not to increase the VGS. We'll try to address this issue. We'll try to see what is going to happen if I keep on increasing VGS in the lab sessions, and we'll see how it is not going to have any impact in the current flowing perspective. Okay. Now let us try to see how this exactly looks from the graphical perspective. Okay, so what I did here, VGS I increased, and I want to see what is going to happen with respect to ID. But yesterday I told, or basically I am telling, whenever you want to ensure the current is going to flow, how does the current flows? Current flows only when you apply VDS. So basically when you apply an voltage like this extra voltage or the voltage between drain and source will ensure the current is flowing. But this VGS is not going to ensure any current, but this VDS is the voltage that is going to ensure there is a current is flowing. But right now I'm going to show you what is going to happen, or will there be any current if I just increase VGS. Let's see that. So I'll try to plot a graph. I'm going to increase VGS. I'm going to see what is going to happen ID. First of all, I don't know whether there will be ID or not if I just merely increase VGS. Secondly, if at all there is a current, will that current be how, or basically how it is going to behave if I keep on increasing VGS? Two things I'm going to understand here. Now, I just try to tell you here how exactly the bridge concept. Now look here. Let's say that this is my bridge. These are the pillars. So let's say initially the bridge is built this way, and then connectivity happens till here, and then connectivity happens again, and then connectivity happens again, and finally the connectivity happens again here. Now, if you see, while the bridge was getting constructed, the people who were working on the bridge, they also were moving from one end to another end, isn't it? Although this bridge was not made open to the public, it was not made open to the other particular people, but the people who were building the bridge, they were able to move from A to B. That means when the channel is itself getting formed over here, look here, when the channel is getting formed over here, what exactly we did? We actually increased VGS, and here channel formed. And we kept on increasing this VGS. What is happening here? Although there is a positive voltages that is coming and settling over here, and it is attracting the negative charges over here from the minority from the p substrates, which are the minority carriers. But what is happening from the source? Look here, there are some additional electrons that are getting pushed over here, and these electrons may jump and try to reach the other end once the channel is completely formed. But although their speed, their content, or the volume of the current flowing from source to drain would be very very minimal, because here your VGS will be always small, because VGS is what basically you apply a small voltage until a channel is formed, something around zero point 0.1 zero point 0.5 volts, 0.6 volts, or 1 volt. But the main concept to understand here is, during the course of formation of channel, there is a small current flowing from source to drain, and that will be a very small current, and that current flows only after channel is completely formed. Let's say that Vt is 1 volt. Upon 1 volt the channel is completely formed. Now you increase the VGS. That VGS is going to strengthen the channel within this portion, but at the same time it is also going to push some extra electrons, and these electrons are moving from source to drain. That means there will be some sort of flow of current. And if I mark this as a Vt, so till Vt there will be no current, and after Vt you can see there is a small exponential rise in the current, and it won't increase beyond a particular VGS. It will be almost a constant even though you increase the VGS. Why? Because there is no point in increasing the VGS, because increasing the VGS is only going to strengthen the channel, and the extra whatever the electrons that are coming over here, and they just hop from one end to another end, because they are of very small quantity. VGS will be in the, like I told, in the range of 0.6, 0.7, 1 volt, 1.5 volt, in that range. And those electrons will not give you a big current to move from source to drain. So this is basically how your graph looks. If you observe here, if you observe, this is, let's say this is, if I mark it here, VGS1, basically let's say that this is 1 volt and this is 2 volt, and let's say this is 3 volts, this is 0 volts. So you keep on increasing the voltage, the current won't increase further, and this can be verified with experiment. So that would be our first experiment to verify the drain versus gate to source voltage, or gate to source voltage versus the drain current. So this is basically the concept that happens with respect to ID versus VGS, because the fundamental aspect of using VGS is to turn on the MOSFET and not to ensure the flow of current. That's it. So this is all about how basically your first set of condition works with respect to VGS. Now let us try to understand what is going to happen with respect to VDS. So let's say this, my two conditions are done. So let's say we have the third condition. If VDS is applied after VGS is greater than VT. Remember this condition. I'm applying this condition of VDS once VGS is more than VT, because obviously now I need to ensure the flow of current, and that can be made possible only if the channel is formed. See, there is no point if I just apply VDS and there is no channel is formed over here. If I haven't applied VGS, that means there is no channel, that means there is no connectivity, and that means the MOSFET can be claimed in its off state. And in its off state, if I apply VDS, that VDS will push the extra electrons and they will not be in a condition to reach the destination drain. So that means whenever you are applying VDS, it is assumed that, or it is by default considered that there was VGS being applied and the MOSFET is on. So basically this condition, VDS is applied only when MOS is on, and one is when MOS is on, when VGS is being applied and it is greater than or equal to VT. Under this condition only you can apply VDS to make it a practically viable thing, otherwise it's a meaningless. Now let's try to understand what is going to happen. I'm going to draw the structure one more time, and I am going to assume that a VGS has been applied, and that VGS, after applying to a certain voltage, it has been locked. Let's say VGS is set to 2 volts, and once it is set to 2 volt, I'm not going to increase the VGS further, because now I know that there is no use in increasing the VGS further, because with that there is nothing going to be achieved. So let's say I am applying VGS of 2 volt. Now here I'm applying some voltage VDS. There is this channel being formed. Now couple of things that we are supposed to understand over here, and this is the condition which is very, very important. Now let's see. Simple. This is a subset of this condition. Let's say 3A. If VDS is increased, simple. Now the bridge is built. Now it is open to the public. And if I increase VDS, that means if I allow more and more public, that means, look here, more and more electrons are being pushed into the source side, and these extra electrons will not be in a position to sit over it here within a small region, and they hop and they move to the drain. So that means if I keep on increasing VDS, more and more current flows from source to drain, as simple as that. So if VDS is increased, more ID flows. Now, the common question. Now, this is the condition when I say the MOSFET is on and current is flowing. So, when I have applied VDS, I say MOSFET is on and the current is flowing. Now, the common question, what is the maximum limitation? Like here, when we applied VGS and figured out if I increase this VGS further, I came out with a conclusion that I cannot increase the VGS further because it won't have any impact. Now, similarly, let's try to understand, can I increase VDS to a large value? Why I want to increase this large value? Because I know that if VDS is increased, drain current will be flowing and that current also increases. So can I not get more current by increasing VDS? Is that not possible? So if this is made possible, then it will be a very biggest invention, right? It will be biggest achievement by simply increasing VDS within the MOSFET. I'm going to achieve more and more current. But is that possible? Can there be a condition where I can achieve this? Let's try to understand this. Now look here, when you try to increase this VDS, let's try to give some numbers over here. Let VDS equal to 0.5. And here I'm assuming in all these cases, VGS is given. See, I will just write for VGS equal to 2 volt. So that is already set. I'm not further increasing VGS. Now, whatever I'm going to do, I'm just going to do with respect to VDS only. So let's say VDS equal to 0.5. Now, when zero point 0.5 volts is applied, that means 0.5 volts equivalent amount of negative charges will accumulate here in the source, and zero point 0.5 equivalent amount of positive charges will accumulate on top of this, or basically they go here inside this particular, they will not go here, they'll accumulate here just nearer to the drain. So here these electrons will be pushed here, they try to sit over here, metallic connections. Some may have a combination over here, but further they won't combine. I'll tell that also, they'll sit over here. Now again, let's try to, and that will ensure that that much equivalent amount of current, whatever that current, let's say, will not quantify that. Let's assume some current flows for this 0.5 volt. Now, second condition, let's try to increase VDS is made to 1 volt. Now, if I increase further, that means this is getting more and more positive, and these are getting more and more negative. Because it's a negative, they can easily push into this region. They hop over here because the moment they reach, they repel, and they can combine over here, and they cannot neutralize, and they repel, and they can hop from one end to another end, and they reach the destination drain. That means for VDS, again, ID, it increases. Now, let's say VDS is 2 volt, ID further increases, and in all the cases, my VGS is 2 volts still here. Now, let's try to figure out what is exactly happening within the MOSFET. Please listen carefully what is going to happen. Now, if you observe, this is basically a P substrate. Okay. Now, if you observe, this is my P substrate. I'm going to write the P substrate here. Okay. And this is my N. I'm going to write here N. Now, are they not internally behaving like a PN junction diode, if you observe? Correct? And more importantly, always remember the P substrate or the body has to be always connected to either ground or to the lowest potential within that particular MOSFET. And here, which is my lowest potential? My lowest potential is -2 volt. That means in one or the other way, I say that the P substrate should be connected to the source. Now, with the question why it has to be connected to source, and why if I do not connect it to the source, what will happen? I'll talk it as a separate content, as a body effect. Now let us try to assume that, or let us try to presume that we know that the P substrate has to be tied to the source. Now, if I just draw the circuit, or if I draw the cross-sectional view, so let's try to make it a little bit large. So if I now try to look here, I have a P-type substrate and I have an N-type drain. Now P is connected to the negative, and where is my N connected? If you observe, N is connected to positive. That means if I look into this entire entity, what exactly you were doing? You were just simply increasing the voltage VDS to ensure more and more current flows. But in the due course of time, we came across a scenario where there is an inbuilt PN junction. And if you see the PN junction, how it is biased, can anyone quickly? How the PN junction is biased? Forward biased or reverse biased? It is reverse biased, right? Because I can say that P is connected to negative side of the battery and N is connected to the positive side of the battery. And in the reverse bias condition, whatever that is going to happen with respect to PN junction diode, the same is going to happen categorically for my this particular MOSFET, because internally it is going to behave as a PN junction diode. Now you are increasing VDS. Now let's say you increase VDS further. Let's say VDS is 3 volt. So that means this is 3 volts now. Indeed, I can say this way. I can write it as, rather than having connectivity this way, because it is actually not connected that way. So P is connected to the volts, right? See, this is my 2 volt. And your N is connected with the 3 volt. So basically here it is plus 2, sorry, minus 2 volt. And here it is plus 3 volt. Whatever may be the voltage, ultimately it is reverse bias, because P side is at a lower potential and N side is at a higher potential. And anyhow, this you are not increasing, you are increasing only this voltage. This is you are increasing, this is varying, because this is already fixed. This is your VGS and this is your VDS, and you are increasing this VDS. So that means initially, if you remember how a PN junction exactly works, PN junction diode, these electrons and holes, they try to diffuse to the other end and they create a barrier, something like this. And now when you apply a voltage, if that voltage is a positive voltage, in the sense if that voltage is making the PN junction as a forward bias, then this barrier would be broken and you say that the diode is on. But in the same case, if it is a reverse bias, what is going to happen? Now if I increase this VDS, what is going to happen? So it is going to push more and more holes and it is going to strengthen the barrier. What is going to happen? If you see here, nothing is going to happen because you are not increasing VGS, it is fixed. But basically what is happening over here, if you see, there's a barrier creation, and that means here within this PN junction, here there will be a barrier that will be created, something like this, and barrier which looks like this. That means there is a clear cut off barrier that is happening, and your drain is partially disconnected with the channel. That means I'll just try to redraw it here, how exactly it looks. Just a channel. This is my N plus source. This is my N plus drain. How exactly the channel looks? The channel looks partially disconnected, something like this. And if you observe carefully through experimentation, you would see that. And here, this is the region where the depletion region of your PN junction region has been formed, and that has resulted in the disconnection of your channel with respect to the drain. So that means if I try to consider this as a small length delta L and this being your earlier length of the channel as L, what would be this one? This would be L minus delta L. That means if you think I can get more current by increasing this VDS, we are absolutely wrong, because the moment I keep on increasing this VDS, there is a reverse bias action of your PN junction would come into picture, and that is going to eat up some portion of the channel over here, and this particular action would disconnect the channel from the drain. And if you keep on increasing this VDS further, and this length of the channel further keeps on decreasing, and that entirely makes the entire flow of the current to come to a standstill. So basically the point here to remember is I cannot increase the VDS further to an extent where the channel is eaten up by the inbuilt PN junction. I'll just try to repeat it. There is an inbuilt PN junction which is in a reverse biased format, and when the PN junction is reverse biased, there is a depletion region that happens within the PN junction, and that depletion region increases further if you increase any particular voltage. In my case, here you are increasing VDS. Here, if you increase VDS, the PN junction depletion region increases, and that is going to eat up some portion of the channel. And the time at which this happens, now if you observe, if we observe what are the contents within the depletion region, if we just see, let's try to see that, let's try to look into these things. What is the content within the PN junction? So what were the things here? This is basically a P, and here your N. Towards the N there will be a formation of positive sides like this towards the N, and towards the P there will be an accumulation of electrons. And if you observe, in fact, let's try to, if you observe which side is more strengthened, which side is more stronger, the positive charges towards the N are stronger than the negative charges towards the P. Why? Because look here, you are not increasing VGS because VGS is fixed, and that is the reason why towards the P the accumulation of negative charges is less, because you are not pumping in more electrons over here. This is already fixed. This is your VGS. But you are increasing VDS, that means you are pumping in more number of holes over here. Although it's a reverse biased, it's imbalancedly reverse biased. The strength of your positive charges in the depletion region is more than the negative charges within the depletion region. The same I am going to depict it over here. So there are a lot of positive charges within the depletion region, and what is going to happen at one particular point of time, at one particular voltage, these positive charges, whatever you can see over here, these positive charges within the depletion region, they just pull all these electrons, because it is positive over here. See, earlier what was the scenario? Earlier this drain was made up of N type material, and the electrons were just hopping from one end to another end in a free flow manner. But right now, this drain, nearer to the drain, there is an accumulation of lot of electrons because of an inbuilt PN junction, and these electrons will be suddenly attracted towards the drain, and as a result, sudden and quick current flows at one particular voltage during which this happens, and that particular voltage at which, that is a particular VDS at which sudden current flows is known as the MOSFET. MOSFET has entered saturation region, and that voltage is known as, any idea? It's known as pinch of voltage Vp. So basically, when a sudden current happens, so what we did here, we are assuming, let's say at VDS equal to 3 volt, this entire thing happened. If I increase further, the pinch off becomes more and more strengthened. So basically, at here in my scenario, at VDS equal to 3 volt. Now at VDS equal to 3 volt, we say pinch off has been reached and MOSFET is in saturation region. Why we say that the MOSFET is in saturation region? Because basically you can see there is a sudden and continuous and constant current is going to flow. Because if you increase the VDS further, there is obviously the depletion region increases, but the flow of current would be remaining same because it has already started to flow suddenly, and that sudden flow of current is going to remain as it is in spite of increasing VDS. That means no matter further you increase VDS, at one point of time the current is going to remain as a constant, and that is why we say that the MOSFET has entered into a saturation region. So if I want to draw the graph of that particular thing, it would look something like this. This is my VDS. I'm increasing the VDS, and let's say what is going to happen with respect to ID. And all these are happening for VGS equal to 2 volts. We should mention that also. All these are happening at a for constant VGS equal to 2 volt. So initially, when you keep on increasing the voltage, the current starts to increase, and once the condition of pinch off is met, the current is going to ensure it is going to remain constant. Constant in the sense there is a small increase, but it won't be rising very steeply. There is a small incremental rise, but that small incremental rise will be very small. So that is what is going to happen with respect to your current. So this is the graph of ID versus VDS, and the point at which the current is going to remain constant and the point at which the current is entered into a saturation region is your pinch off point. And the region after the pinch off region, so this portion, so this entire region is your saturation region because current is saturated. And before the saturation region, whatever you see, which is over here, that you can say it as a triode region or linear region. So these are the two main regions of operations. And there is one more region, cutoff region. Cutoff region is nothing but when cutoff indicates when MOSFET is off, or basically when VGS is less than VT. So that's your cutoff condition. So this is basically how your entire MOSFET is going to behave when you try to increase VDS at a fixed VGS. And in due course of time, it is going to reduce the length of the MOSFET also from L to L minus delta L. There is a small reduction in the length. But of course, that can be taken care. That is altogether a different ball game. So I'll try to explore that about a little bit later. And even I try to explain about why we connected this to the source. Why not? If we do not connect this, what will happen? That also I'll try to tell you. So to summarize, so basically MOSFET is said to be on when VGS is greater than VT. And if I keep on increasing VGS further, there is no impact. The current is going to remain as it is, and the graph would look something like this. And if I apply VDS, once my VGS has been applied and try to increase this VDS, the current starts to increase. But that current increase will not be forever, and that current increase would reach a saturation point at a particular voltage of VDS known as a pinch off voltage, or I can say it as a saturation voltage. So this is basically pinch off point or pinch off voltage, or I can say VSAT, the saturation point. So to look into the graph would look like this: VDS versus ID. So basically, if I want to further write down the set of conditions, so there are basically two conditions which will define that it is in the saturation region and in the triode region. First is VGS is greater than VT. That is has to be MOSFET will be in its on state. Once this is achieved, that is this condition, VDS, if it is greater than or equal to VGS minus VT. In fact, I will not say greater than or equal to, it will be conflict. So I'll just say VDS greater than VT. So this is basically your saturation. So if I just see this condition over here, so what is your VGS here? VGS is equal to 2 volt, and let's say VT is equal to 1 volt. And what was the VDS we applied over here at which this particular thing happened? It was 3 volts. So 3 volt, and if I try to put it in this condition, VDS, check whether VDS is greater than VGS minus VT. If that is the scenario, let's say whether this is going to work. VDS is 3 volt, VGS is 2, VT is 1. So definitely this is going to get satisfied. So that means the MOSFET is in its saturation. So that means to identify when exactly MOSFET enters into saturation, or to identify when this entire pinch off scenario happens, the conditions are there. The conditions are, this can be obtained through the trial and error method experimentation, where you keep on increasing VDS and you keep on changing VGS, and you can see that at one particular point there is a condition where this entire thing happen, and that condition would be definitely VDS greater than VGS minus VT. But if let's say VGS is 2 volt and VT is 1 volt, and let's say VDS is 0.5 volt. Now let's apply the condition whether VDS is what? VDS is 0.5 and VGS is 2 minus 1. So that means it is lesser, right? Here it is 1 volt and it is 0.5. And that condition, it will be in its linear mode of operation, or linear region. That means, or triode region. That means it has not yet entered the saturation. So always remember these conditions, and all these conditions, whatever I am talking. So I can write here VDS less than VGS minus VT. That will be in its triode region, and all the conditions whatever I'm writing over here, these are all for N MOSFET, considering NMOS. For P MOSFET, the conditions would immediately reverse. So this is basically the region of operations and how the graphs would look, and what are the set of conditions, and how to apply, what to apply. Everything has been detailed over here. So that's it from this particular session. So we'll try to get up with some of the experimentations on how exactly these graphs can be achieved, and how exactly we can get into the realistic value by plotting VDS and ID, and VGS and ID. So all these things we'll try to take up in the next session. So that's it from my end. So if you have anything to ask, you can ask. Any doubts, you can ask.